You write code on your machine, it works perfectly, and you ship it to a colleague. Same code, same language, but it crashes. This is the classic "it works on my machine" problem, and for years it made deployments a nightmare. Docker was built to solve exactly this problem by packaging your app with everything it needs to run. In the next few minutes, we'll go from zero to actually understanding how Docker works under the hood. Images, containers, volumes, networks, and Docker Compose, all explained with real diagrams and real code. Before Docker, the standard way to isolate an application was a virtual machine. A VM emulates an entire computer, its own kernel, its own operating system, gigabytes just to boot. A container is radically lighter. It shares the host machine's kernel and only packages the application and its dependencies. That means a container starts in milliseconds, not minutes, and uses a fraction of the memory. You can run dozens of containers on a laptop that could barely run 3 or 4 virtual machines. That efficiency is the entire reason Docker exploded in popularity. So what actually is Docker mechanically? It has 3 core pieces: the Docker client, the Docker daemon, and a registry. The client is the Docker command you type in your terminal. It talks to the daemon, a background process that does the real work, building, running, and managing containers. And the registry, like Docker Hub, is where ready-made images are stored and downloaded from. Client, daemon, registry, that triangle is the whole engine behind every Docker command you'll ever type. Everything in Docker starts with an image. An image is a read-only template, a snapshot of a file system plus instructions on how to run it. But an image isn't one giant blob, it's built from stacked layers. Each instruction in a Dockerfile adds one layer on top of the last. And layers are cached. If you only change your application code, Docker reuses every layer below it instead of rebuilding from scratch. That caching is why a second build can take 2 seconds instead of 2 minutes. A container then is just a running instance of an image, with one thin writable layer added on top. Let's actually write one. A Dockerfile is a plain text recipe, a list of instructions Docker follows to build your image. From picks a base image here, a slim Python runtime. Workdir sets the working directory inside the container, and copy brings your source code in. Run executes a command at build time, typically installing your dependencies. Expose documents which port the application listens on, and env sets environment variables available inside the container. And cmd defines what runs when the container actually starts. 7 lines and you've fully described how to package your entire application. With that Dockerfile written, building the image is one command. Docker build, a tag for the image name and a dot for the build context, the current folder. Docker reads the Dockerfile top to bottom and executes each instruction inside a temporary container, committing the result as a new layer. You'll see each step print in your terminal, layer by layer, until the final image is tagged and ready. Run Docker images and there it is, your application fully packaged sitting on your machine. From here, that exact image will run identically on any machine that has Docker installed. An image is inert until you run it. Docker run starts a new container from that image. The D flag runs it in the background, detached from your terminal. P maps a port on your machine to a port inside the container, here 8080 outside to 80 inside. Without that mapping, the container is completely isolated. No traffic from outside can reach it. Docker PS lists every container currently running with its ID, its image, and its status. Docker logs shows you everything the container has printed, which is usually the first place to look when something breaks. Docker exec drops you inside a running container with a live shell, as if you'd SSH'd into it. And Docker stop, followed by the container ID, shuts it down cleanly. There's a catch: a container's writable layer disappears the moment the container is removed. Any data written inside it, a database, uploaded files, is gone with it. Volumes solve this by living outside the container's lifecycle, managed directly by Docker. You mount a volume into a container with V, and anything written to that path persists on the host. A named volume is managed entirely by Docker. A bind mount instead points straight at a folder on your own machine. Stop the container, remove it, start a brand new one with the same volume, and the data is still there. That's what makes Docker viable for anything stateful, like a real production database. By default, Docker gives every container its own private network. Containers on that same network can reach each other directly by name without any extra configuration. Your API container can simply call the database container by name, and Docker resolves it automatically. That built-in DNS is what makes multi-container applications so easy to wire together. Expose a port to the outside world only when you actually need external traffic to reach it. Everything else stays private, invisible outside the Docker network. Real applications rarely run in a single container. You've got an API, a database, maybe a cache. Running each one by hand with the right flags in the right order gets old fast. Docker Compose lets you describe your entire application, every service, in a single YAML file. Each top-level key is a service, with its own image, ports, and volumes. One command, Docker Compose up, builds and starts every container, wires up the network between them, and streams the logs. Docker Compose down tiers the whole thing back down just as cleanly. For local development, Compose is often the entire workflow. Once your image works, you'll want to share it. Docker Push uploads your image to a registry, most commonly Docker Hub. From there, anyone, a teammate, a server, a cloud platform can pull that exact same image with Docker Pull. Because it's the same image, byte for byte, there's no "it works on my machine" left to argue about. That's the promise Docker actually delivers on. A few habits separate a good Docker image from a bloated one. Start from a slim base image. Alpine or slim variants can be 1/10 the size of the full one. Use a .dockerignore file so build artifacts and dependency folders never even reach the build context. Order your Dockerfile instructions from least to most frequently changing so the layer cache actually helps you. And for compiled languages, use a multi-stage build. Compile in one stage, then copy only the final binary into a tiny runtime image. That one trick alone can shrink an image from a gigabyte down to a few dozen megabytes. Run your process as a non-root user whenever you can. It costs one extra line and removes an entire class of container escape risks. Small images pull faster, start faster, and have a smaller attack surface. This is why Docker sits at the center of modern software delivery. Every major cloud platform, Oz, Google Cloud, Azure, runs containers as a first-class citizen. Continuous integration pipelines build a fresh image on every commit and test it in complete isolation. Kubernetes, the tool that orchestrates containers at massive scale, assumes Docker-style images as its basic building block. None of that infrastructure exists without the simple idea we just walked through: package once, run anywhere. Let's recap what actually happened here. A Dockerfile describes your application as layered instructions. Docker build turns that into an image. Docker run turns that image into a live container. Volumes keep your data safe, networks connect your services, and Compose ties it all together. That's the whole mental model, and now you actually understand what's happening every time you type Docker run.